On page 7, we're going to change gears and start talking about logarithmic equations. The good news is that these equations are super easy to identify because they're equations that have logarithms. So just like we saw with exponential equations, that there's multiple types of exponential equations, there are going to be multiple types of logarithmic equations. So we are going to begin by talking about how to solve a logarithmic equation that can be written in this format. Log base A of m is equal to n. Okay, so let me translate this little math statement here. Okay, the instructions that follow in this box are going to be for logarithmic equations that you can write in this format. Okay, a logarithm, doesn't matter what the base is, but some logarithm, one logarithm, I'll even put that one logarithm equal to a number. Okay, the equation may not come written exactly like that, but you can manipulate the equation to be one logarithm equal to a number. Okay, so let's read how to do this and then we'll do some examples. Okay, in step 1, if necessary, move all logarithms to one side of the equation and all other terms to the other side. Then you're going to condense the logarithms into a single logarithmic expression using the major properties of logarithms. Okay, if you glance back to the bottom of page 3, those 3 major properties that I'm talking about are these guys, okay, down here, okay, these 3 guys, okay. So you would use, if necessary, those 3 properties to combine your logarithms into one logarithm. Okay, so then picking up with step 3, you're going to simplify the other side of the equation and it should be just a single number. And then after steps 1 through 3, that should have resulted in an equation of the form log base A of m is equal to n. Okay, meaning one logarithm is equal to a number. Now we're going to use the definition of a logarithm to rewrite the resulting equation as an exponential equation. Okay, recall that log base A of m is equal to n is equivalent to saying that a to the n power is equal to m. Okay, so step 4 is saying once you have your equation in the format one logarithm is equal to a number, apply the arrow definition of a logarithm. Okay, that's going to get rid of the logarithm. So in step 5, you're going to be able to solve for x. Okay, step 6, remember with exponential equations, it's not a requirement to check your solutions, but you really need to check your solutions when you're dealing with a logarithmic equation. So step 6 says to check your solutions in the original equation. You're not trying to see if you're right or wrong. You're more worried about you may get something called an extraneous solution. So it's something that looks like a solution, but it really isn't. So you need to exclude any solution that leads to taking the logarithm of a negative number or of 0. Okay, so remember that you have to check your solutions after solving an after solving a logarithmic equation, because you may end up with something that looks like a solution, but once you plug it back into the original equation, it causes you to take the logarithm of a negative number or of 0, and that's bad, 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 so you have to get rid of it. Okay, so let's try some of these out. Okay, so in example 3, it says solve each equation, give both the exact value or values for x and a decimal approximation to the nearest thousandth. Okay, so the equation in part A says 4 times the natural log of x is equal to 36. Okay, we're trying to figure out what value of x makes this a true statement. Okay, so basically you can quickly identify this as a logarithmic equation because you see a logarithm, the natural log of x, in this statement. Okay, so what we just said in the box above, we can apply this process if our equation looks like one logarithm equal to a number, okay? And that's pretty much what we have, but the logarithm here, I've highlighted in yellow. We need to isolate that guy. See how there's a 4 in front that's multiplied up front? We need to get rid of that, okay? So we're going to isolate the natural log of x. We're going to divide off the 4, okay? Whatever you do to one side, you have to do to the other. So this is going to tell us that the natural log of x is equal to 9, okay? So now we have an equation that fits the bill. We have one single logarithm is equal to a number, okay? So at this point, we're going to get rid of the logarithm by applying the arrow definition of a logarithm. We know this is natural log, so the base is e, and if we do the arrow thing, we know that e to this power is equal to this, okay? So this is going to tell us that e to the 9th power is equal to x, okay? Guess what? We're done, okay? X is equal to e to the 9th. This is the exact answer, okay? If you take e and multiply it by itself 9 times, that's the value of x that works, okay? So here's your exact answer. We can go to a calculator to get a decimal approximation, okay? So we're just going to pop in e to the 9th power, okay? So we're going to get, if we round this to the nearest thousandth, we have the, after the decimal place, we have tenths, hundredths, thousandths. So we're focused on this 3 because there's a 9 behind it. We need to bump up the 3 to a 4. So it's going to be, the answer for x is 8,103.084. Okay, there's your decimal approximation, and we're done. Okay, so the gist of doing this, okay, if you were able to get your logarithmic equation in a format so that you have one single logarithm is equal to a number, once you have that, you're gonna apply the arrow definition of a logarithm to get rid of the logarithm. Okay, all right, let's try another one. Okay, in part B, we have log base 7 of x cubed plus 65 is equal to 0. We are trying to solve for x. What value or values of x make this a true statement? Okay, clearly this is a logarithmic equation. Okay, the great news is that the logarithm is isolated already. Okay, you've got the logarithm of all this stuff, but at the end of the day, on the left side, this is one logarithm. It's by itself on one side of the equation. Okay, so we can go ahead and just apply the arrow definition of a logarithm. Okay, if we take the base and raise it to this power, meaning 7 raised to the 0 power, that has to give us this quantity, which is x cubed plus 65. Okay, the logarithm is gone. Okay, so we're going to have to solve this now for x. Okay, so let's go from here. Okay, anything to the 0 power is 1. Okay, so we get 1 is equal to x cubed plus 65. Okay, so this is an equation we know how to solve. Okay, so I need to get the x by itself. This is not an exponential equation. Okay, so we're just going to try to isolate the x here. So we're going to move the 65 over. So I'm going to subtract 65 from both sides. Okay, this is going to tell me that negative 64 is equal to x cubed. Okay, and then I'm just going to switch sides here. So I'm going to get x cubed is negative 64. Okay, we want x, not x cubed. So to get x, we've got to take the cubed root of both sides. Okay, whatever you do to one side, you have to do to the other. To undo a cube, you're going to take a cubed root. So on the left, the cube and the cubed root cancel, leaving you with x. And then on the right, the cubed root of negative 64 is going to be what? Well, it's going to be a number that you multiply by itself 3 times to get negative 64. So that answer is negative 4. Okay, so here's your answer. You're done. Okay, we do need to check our answer. Okay, and I actually forgot to do that in part A, so I'll go back and do that after this, okay? If we check ourselves, okay, it's not like we're trying to make sure, oh, -4 is the correct answer, maybe I solved this wrong. We're worried about plugging in -4 to the original equation and that causing us to take the logarithm of a negative number or of 0. Okay, so let's go back and pop -4 in for x into the original equation. We're going to get log base 7 of -4 cubed plus 65. Okay, so if we simplify inside the parentheses, we're going to be taking the logarithm base 7 of -4 cubed is -64 plus 65. We'd be taking the logarithm base 7 of the quantity 1. So that's okay. If you plug in -4 for x, you're not going to get an error, okay? So we're okay. -4 is indeed the solution, okay? Let me go back up here and check for part A. We got a solution of e to the 9th, okay? I'm just going to plug it into the logarithm piece to make sure I don't get an error, okay? So I'm going to have 4 times the natural log of e to the 9th. You're taking the logarithm of e to the 9th. That is a positive quantity, so we're not going to encounter any error. Okay, so this is good. E to the 9th is a valid solution. Okay, let's take a look at the equation in part C. Okay, we have log base 3 of 4 times x plus 1, that quantity times x plus 1. We're taking the logarithm of this entire quantity. Okay, so the logarithm equals 3. Okay, so here we have a logarithm. This is a logarithmic equation, and the great news is that we have a single logarithm. This is one logarithm equal to a number. Okay, if we're dealing with just one logarithm equal to a number, we can jump straight to the arrow definition of a logarithm. Okay, so here this means that 3 to the 3rd power is equal to this quantity. Okay, so 3 to the 3rd power is going to be equal to 4x plus 1 times x plus 1. Okay, the logarithm is gone. Okay, we can solve for x. Okay, we're going to be left, let's go ahead and see how we would handle this particular equation. It is not exponential, it's just a regular old equation. Let's solve. 3 cubed is going to be 27. I'm going to go ahead and multiply out what's on the right side here. Okay, so you have to use FOIL or box this. 4x times x is going to give you 4x squared. And then 4x times 1 is 4x. And then 1 times x is going to be x. And then 1 times 1 is 1. Okay, so just a quick scan here. This looks like I'm going to be left with a quadratic equation. The highest power of x in the whole thing is the 2nd power. So I need to combine like terms and set one side equal to 0, and then I will either factor or use the quadratic formula here. Okay, so let's see here. We're going to get 27 is equal to 4x squared plus 5x plus 1. Move the 27 over. I'm going to get that 0 is equal to 4x squared plus 5x minus 26. All right, so we can either factor the non-zero side or we can apply the quadratic formula here. This one might take a few minutes to factor. You have to play around with it. So I'm just going to go ahead and use the quadratic formula. A is the number in front of x squared, so it's 4. B is the number in front of x, so it's 5. C is the constant, so it's negative 26. To get x, I need to do negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So let's go ahead and simplify. We're going to get negative 5 plus or minus the square root of, I'm going to go to my calculator and compute what is underneath the square root. So let's see here. We're going to get 5 squared minus 4 times a times c. Okay, so that's going to tell us that there's 441 underneath the square root sign. Okay, we're dividing by 8. Okay, and let's go ahead and see if this square root simplifies. This is going to be negative 5 plus or minus the square root of 441 is going to be 21. Okay, so this is going to be negative 5 plus or minus 21 over 8. Because of the plus or minus, we're going to end up with two solutions. Okay, so let's see here. The first value of x that will work here is going to be negative 5 plus 21 over 8. The second solution is going to be negative 5 minus 21 over 8. So I just chose, one solution comes from choosing the positive in the middle, the other comes from choosing the negative. So now let's simplify. Okay, so negative 5 plus 21 is going to give us 16 over 8, which is 2. So x equals 2 is one of the solutions. The other guy, negative 5 minus 21 is negative 26 over 8. Both of these numbers are divisible by 2. So this simplifies to be negative 13 over 4. Okay, so these are your two potential solutions. X equals 2, x equals negative 13 fourths. We've got to go back and check these guys out. Okay, so I'm running out of room. I'm just going to go up here. Okay, again, you're worried about plugging in a solution, and that will lead to taking the logarithm of a negative number or of 0. Okay, so if x equals 2, what happens? Plug into the original equation. We're going to be taking the logarithm base 3 of 4 times 2 plus 1 times 2 plus 1. Okay, so this is going to be the logarithm base 3 of 8 plus 1, which is 9, times 3. So this is log base 3 of 27. You're taking the logarithm of a positive number. You're good to go. Okay, let's check the other potential solution. This time the x value is negative. So let's check. Plug it in for x. Log base 3 of 4 times negative 13 fourths plus 1 times negative 13 fourths plus 1. Okay, let's see what happens if we simplify. This is going to be log base 3 of, let's see, the 4's would cancel here. That's going to be negative 13 plus 1. That's going to be negative 12 times, let's see, negative 13 fourths plus 1 is going to give us negative 9 fourths. Okay, so you're taking the logarithm of a quantity. It's a negative times a negative, so this is actually going to be a positive number. If you simplify these guys, this is going to be log base 3 of negative times negative is positive. 4 goes into 4 once, 4 goes into 12 3 times, so this is also going to be log base 3 of 27. You're good to go here. Okay, so both of these solutions work. Okay, so we get two solutions. I'm going to write them over here. X equals, what did I say? X equals 2 is the first solution, and the other guy is x equals negative 13 fourths. Okay, here are the answers.